Good morning, students. Welcome to the mass transfer course. So we have completed two chapters. The chapter 1 was introduction and motivation, and second chapter was molecular diffusion. So today we will start our third chapter or third topic, that is convective mass transfer and mass transfer coefficients, and today's lecture will be lecture 9. Already we have studied the basic definition of convective mass transfer, and the definition was mass transfer occurring under influence of motion of fluid medium is called convective mass transfer. It is very much similar to your convective heat transfer, and here one important term is influence of motion of fluid. So fluid mechanics is involved. And in molecular diffusion we have developed the theories where medium was stagnant, and in convective mass transfer there will be motion in fluid. And already the examples we have taken, that is dissolution of sugar cube under stirring condition into the glass of water. And already we have discussed that if you take a glass of water, okay, and if you put one sugar cube, nowadays you will get sugar cube in market. If you put this cube into a stagnant water, then you can visualize this phenomena. Sugar cube will slowly goes into the water, and under stagnant media it will take time, let's take half an hour, and this is happening because of molecular diffusion. And again, if you do the same experiment, means if you take glass of water, you put one sugar cube and you start stirring with a spoon, then what will happen? Because of fluid motion, the sugar molecule will dissolve very fast into the water, and it will take only 1 minute. So here there we are taking the 30 minutes time in a stagnant media, and here it will take less than 1 minute. So here this phenomena, mass transfer phenomena, is very fast. Similarly, we have taken another example, the spreading of perfume molecules when fans are on in a closed room. Okay, when fans are off in a closed room, then perfume molecule is diffusing, that is under stagnant media, that was the molecular diffusion. But when the fans are on, that means it is fluids are under motion. In this case, fluid is in gas phase. Okay, air is fluid. So if it is happening, then you will see the spreading of perfume molecule is very fast. So these phenomena we already experience, it will happen, but we have to know what is the science behind this, why this is happening. If we understand this, why this is happening, then we can use this understanding toward some industry. So, and that's why I am telling convective mass transfer is significant faster than the molecular diffusion. That means If you mass transfer happens under convective mass transfer mode, then you can separate the molecule easier way in a small equipment. Now if you take this example of dissolution of sugar, so let's say this is one sugar cube, okay, and we put this sugar cube into the water. Then if you just take one side, what is happening, that is this is the bulk fluid, and there will be one boundary layer between this sugar cube, that solid material, to this, and you are already familiar with boundary layer theory. So if this is boundary layer will form, then this is the surface of crystal in contact with liquid, and in this here, that surface concentration, this will be a surface concentration of soluble solid A, that is the sugar cube. This is the surface concentration, and this is the bulk concentration. So mass transfer driving force will be that Cs minus Cv, and surface concentration will be saturation concentration of the liquid. Okay, and this is the bound. And if this fluid is stagnant, then this is the case where diffusion of A through non-diffusing B, because here A is diffusing from cube to this liquid. So we know in a molecular diffusion phenomena, Na will be dA by B by L in by 1 by x dN into Ca0 minus Cal. Okay, and this L is the thickness of this one. This is your L. This will be your L. In case of your, this is the boundary layer, stagnant layer. But when you are stirring, what is happening? Then what will happen? This boundary thickness, it will reduce. So if it is reduced, then this term, if this term will reduce, okay, then flux will increase, and that's why if flux are increasing, that's why your molecule are getting dissolved fast. So you know this one. So if you have a high Reynolds number, if you keep high Reynolds number, or if you have a high velocity, then boundary layer thickness will reduce. This understanding you already have in fluid dynamics, and with using this understanding, you have studied the heat transfer coefficient. Same phenomena is happening here, and that's why I am telling the mass transfer Na equal to Kl Ca0 minus Cal. Okay, in this case, in case of turbulent flow, this is the mass transfer coefficient, Kl. Okay, now what is the Kl? Kl will be dOB. This will be, instead of L, it will be delta, boundary layer thickness at turbulent condition or motion condition, by 1 by x. So this is the, if you see the heat transfer, that Qx flux, heat flux is equal to AC Th higher temperature to TL lower temperature. And in case of mass transfer, that is the mass flux kilomole per meter square second. This is the Kl, and this is the Ca0 higher concentration. This is Ca0 minus Cal. Okay. So actually in convective mass transfer, what is happening, the difference between convective mass transfer and molecular dependent, it is nothing. In convective mass transfer, the boundary layer thickness is decreased. If this is decreased, then the resistance becomes low, and if resistance becomes low, then the mass transfer flux will increase. Same phenomena is happening in heat transfer also. And in this case, the same thing will be, this is the expression for the molecular diffusion, and we can do this through the theory, because L here is the boundary layer thickness under stagnant medium, and when it will be fluid, this boundary layer will decrease, and if L decrease means that flux will increase. That's why in case of convective mass transfer, the mass transfer flux is very high, and corresponding this coefficient, that is called mass transfer coefficient, and it is very much similar to your heat transfer coefficient. And in this case, what is KL? KL equal to DAB by delta into 1 by XBM. This L will be replaced by the thing. See, molecule DAB, the diffusivity does not change with the fluid dynamics for the fluid, because it is a function of temperature, pressure, viscosity, other things. Okay, not the fluid volume. XBM, it will not change. Okay, CAG, only thing what I am doing, by studying, I am reducing this boundary layer thickness. Okay, and already you have this concept in your transfer, nothing else, but we are applying this thing in case of mass transfer. So convective mass transfer, you understand, because mass transfer happening under motion of fluid, and when there is a fluid flow, the boundary, if fluid flow is high or velocity high, then boundary layer thickness will decrease. Boundary layer thickness will decrease means that mass transfer flux will decrease, and this is proportionality constant. It is called the mass transfer coefficient. It is very much similar to your heat transfer coefficient. Now let's see this mass transfer coefficient in something other way. Okay, so mass transfer coefficient can be defined in this way. Okay, so mass transfer coefficient is defined on the following phenomenological basis. Phenomenological basis means, you understand, that is coming from the experience. Just I told that, we know that if you put your if you go in our family, okay, grandmother, she knows very well that if you put one sugar cube, it will take a long time to dissolve, but stirring with a spoon, it will do it. It will be quick. They know this phenomena, but they don't know behind what is the reason. That's why this is called phenomenological experience. So what is this? Rate of mass transfer is proportional to is concentration driving force. That is the difference in concentration. Rate of mass transfer means kilomoles per second. Okay, and rate of mass transfer is proportional to area of contact between the phases. If area is high, then rate will be high. Okay. So then I can write WA equal to rate of mass transfer kilomole per solute, and delta C is the concentration driving force between 2 points, and if A is the area of mass transfer, that WA proportional to A into delta C, or WA equal to Kc into A into delta Ca, and this Kc is called proportionality constant of this phenomenon equilibrium, and this is called the mass transfer coefficient. Similarly, you got in your heat transfer coefficient also. Okay. Now, if this is the rate, W is the rate, kilomole per second, A is flux, kilomole per meter square second. So, WA equal to A into Na, because this is A area meter square, this is kilomole per meter square second, so then it will be kilomole per second. Now what is W? W equal to Kc A into delta C. Okay. And then it is concentrated or flux equal to Kc into delta C. So mass transfer coefficient Kc is equal to molar flux by concentration driving force. Okay. If you see, you have studied already heat transfer coefficient Hc, that was the heat flux by temperature driving. In this case, it was temperature, and in this case, it is the concentration driving force. Okay. Mass transfer coefficient is Kc, it is the molar flux by concentration. And similar to your heat transfer coefficient, you have the average local heat transfer coefficient and average heat transfer coefficient. Local heat transfer coefficient means it is a particular point, and if you take the average of this, that will be the average heat transfer coefficient. Similarly, in mass transfer also, there are two types of things. One is local mass transfer coefficient, another is average mass transfer coefficient. Now, in case of your heat transfer course, you have only heat transfer coefficient. There is AC only, because you have a driving force was that was the delta T, temperature difference. Okay, but here already you have studied that what are the different types of concentrations. Concentration I can express as a gas phase partial pressure, mole fraction, then concentration, moles per volume, kilomoles per volume, then liquid phase, mole fraction. There are so many varieties of that. So I can express this driving force, concentration driving force, in different way. But in case of heat transfer, it was delta T. There is no much change. But here it can be expressed in different form. Okay. So that's why in mass transfer there is not a one mass transfer coefficient. There are more than one mass transfer. But in case of your heat transfer, it was one. Again, in case of mass transfer, there are two things already we have discussed: diffusion of A through non-diffusing B and equimolar counter diffusion. So for this also that there will be change, and that's why there are number of mass transfer coefficients. Okay. Now how many number of mass transfer coefficients, that let's see. So different mass transfer types of mass transfer coefficient are defined depending on whether it is a case of diffusion of A or through non-diffusing B or case of counter diffusion. Okay. Whether mass transfer occurs in gas phase or liquid phase. Okay. Because gas phase we have taken another type, liquid phase it will be different type, and choice of driving force. So based on these three things, there are different types of mass transfer coefficient. But in heat transfer there is only one heat transfer coefficient, one is C. But let's see how many mass transfer coefficients are there. So let's take the first case, the diffusion of A through non-diffusing B. So the diffusion of A through non-diffusing B, there are two categories. One is gas phase, another is liquid phase. So mass transfer in gas phase will be A when it is the driving force is partial pressure difference, PA1 minus PA2. That corresponds to mass transfer coefficient equal to small kg, small k capital G, subscript will be capital G. If the driving force is mole fraction, means y1 minus y2, that's small k into small y. and if it is a concentration moles kilomoles per meter cube difference, then it is small kc. So for diffusion of A through non-diffusing B for mass transfer in gas phase, there are three mass transfer versions: small k, small kg, small ky, small kc. There are three types of possibility driving force you can express on this thing. Mass transfer in liquid phase, when that is mole fraction will be, in case of gas phase we took the convention YA, okay, in this XA1 minus X2 correspond to KX, and concentration in liquid phase CA1 minus CA2, that is the KL. So in case of diffusion of A through non-diffusing B, there are 5 mass transfer coefficients according to their driving force and whether it is mass transfer happening in gas phase and liquid phase. Okay, so here Kg, Ky, Kc, Kg, Ky, Kc are the gas phase mass transfer coefficient, Kx and Kl is the liquid phase mass transfer coefficient. Okay. Now, what will be the unit of Kg? Kg, this is I know kilomole per meter square second divided by delta P. Let's take for this one will be kilomole per meter square second by delta Y. A Ky, kilomole per meter square second by delta Y. Okay. Similarly, it will be like this. So it will, I will come later also, then you will understand. Okay. This is the diffusion of A through non-diffusing B. The second type is equimolar counter diffusion. Equimolar counter diffusion also there are gas phase and liquid phase. Okay. So in gas phase we are keeping Kg prime, that is Kg, that is Kg prime, Ky, Ky prime, Kc, Kc prime. Okay. And in a liquid phase Kx, it is Kx prime, this is Kl, so Kl prime. So what are the prime mass transfer coefficient? So that is applicable for your counter diffusion, equimolar counter diffusion, and this one. So you can understand there are 10 types of mass transfer coefficient. Now you have to handle this. Now you may ask that why we need so many mass transfer coefficient? Because that depends on the particular problem. In one problem, you don't know the driving force. What driving force or in what form it is given, according to you need this mass transfer coefficient. If driving force is in terms of pressure, then you have to use that corresponding mass transfer. If it is a mole fraction, then corresponding mass transfer. If it is kilomole per meter concentration, molar concentration, accordingly you use this mass transfer. So in gas phase and liquid phase. So there are 14, we have seen 1, 2, 3, 4, 5, 5, 5, 10 mass transfer coefficients. Now, so let's take the diffusion of A through non-diffusing B. Okay, this is a case. Now what I am trying to, I am comparing this thing with our molecular diffusion. What are the calculation we have done in case of molecular diffusion and what we are getting now, that will make this one. So if you see, if you take the diffusion of A through non-diffusing B, and in for gas phase, in gas phase, A equal to DAB into P RTL PBM PA1 minus PA2. Already we derived this equation for molecular diffusion. Okay, and then if you take this one into this is y1 minus yt, then it will be the p square pb. Okay, and if you take the concentration CO1 minus CO2, that will be that expression. Already we have derived this equation when we calculated this flux, molar flux in case of molecular, and that was the L. Okay, and for liquid phase, Na already DAB rho by m average L xpm x1 minus x2, it that is equal to DAB L xpm cm. I am not telling this thing. If you just cross check your whatever we have made the calculation, you see your node, that you will see in molecular division all these things we have calculated. Now here if you see in case of mass transfer of its gas phase, Na equal to kg into Pa1 minus P2. So the driving force is same. So what is kg? Kg will be DAB P RT. In case of L, that will be delta into by PBM. Only L will be changed. In case of L, it will be the boundary layer thickness, that is delta, and you understand this delta is much lower than this your L. Now this will be your kg. So what is the expression of kg? So this is the expression of the kg. Now if you see that ky equal to y1 minus y2, that is this one. Okay, so ky will be this term, that is DAB P square RT, that L will change to delta into PBM. And if you see that Kc into CO1 minus Ca2, so this was the expression, so this is equal to Kc equal to DAB P by delta PM. Okay. Now for liquid phase, that is Na equal to Ky into x1 minus x2, x1 minus x2, so Kx equal to DAB rho by m average by delta x. This will be this, and KL Ca1 minus Ca2, that will be this, so KL equal to DAB delta by x. So we got now the expression of the mass transfer coefficients Kg, Ky, Kc, Kx, K. Now if you have a, let's take Kc, what is Kc, relation between Kc and Kg? So Kc, if you multiply Kg into RT, then it will cancel out, then it will be Kc, so Kc equal to RTg. Similarly, Ky into Kg, Ky into Kg, P square is there, so if you multiply P, then it will be this. Kx equal to this thing, you have to KL into this term, that will be your Kx. So this is, so this is the relation between the mass transfer coefficients. So that is very important. If you see, let's take a problem, you have given the gas phase, or you have given the driving force in terms of mole fraction, and let's take you have given the mole fraction in this, and you have given the that mass transfer coefficient in kg. So then you have to, for this problem, you have to express, you have to, that kg you have to convert into ky, and this is the conversion factor. If you multiply it with k, then it will come. Okay. So here you have to little bit smart enough to tackle this different type of mass transfer coefficients depending on the particular problem. Okay, you need to rearrange this. Sometimes you have to change your driving force, sometimes you need to change your mass transfer coefficients. Okay, so because what masses, if in a problem if you are giving this driving force in terms of mole fraction and mass transfer coefficient of kg, then because in this you have to use the ky, not kg, because kg ky there is a difference, and this is the way you can calculate this one. So if you can remember this thing, and so then if you see all these things, if you know one mass transfer coefficient, another mass transfer can be calculated. Now here if you see, let's say kg equal to dab into p rt delta pb. dab it is known, okay, p by particular rt known, pbm also will be known because ca1 ca2 you know the delta. So other than, if you see in this case, you can calculate the mass transfer coefficient easily if you know the value of delta. Delta is the boundary layer thickness. Because except this delta term, other parameters are easily accessible. For a problem, you can get it. This is, and getting this delta, that is thermal, the boundary layer thickness, that is very difficult. Still now, no theories are developed which can predict the accurate boundary layer thickness delta, and this is the most uncertain thing, and because of that, okay, you know how to calculate the transfer coefficient. Transfer coefficient is equal to what? K thermal conductivity by delta. Thermal conductivity is known, but delta, getting accurate delta from theory, not possible, and that's why they have used some correlations, and you know that the famous correlation is detailed vector equation. Similarly in mass transfer also, that because of this problem, because calculation of delta is not what, it is still no theories can predict this delta accurately, so there is a gap, but somehow people are managing this way using this some empirical correlations and with the use of dimensionless number. That will come later, but here we are given the relations where if you know one mass transfer coefficient, other mass transfer coefficient can be calculated, and what are the expression of the different mass transfer coefficients that we have presented here, and why we cannot, it is difficult to calculate mass transfer because only the problem is delta, boundary layer. Already you know this one, because you have studied the mass transfer, fluid dynamics and your heat transfer problem. Similar cases. So similarly for equimolar counter diffusion. So equimolar counter diffusion for molecular diffusion RT, DAB or RTL, PO1 PT, P2, DAB RTL P into, this is the expression. So per pressure, set pressure in terms of driving force, or driving force in terms of mole fraction, this is the molar concentration. Similarly for liquid phase, this is mole fraction, this is the molar. And already we have defined this, that kg prime, ky prime, kc prime, kx prime, kl prime. So kg prime will be what? This one, DAB RT in case of L. So in molecular diffusion, that is the L. Okay, that boundary layer but when it is will be fluid under flow, that will change, it will reduce. Okay, here delta is much lower than the, okay, delta qi will be what, this one only, this dab p rt by delta, kc dash, kc prime will be dab by delta. You can understand dab by delta, and you can remember mass transfer coefficient hc equal k by delta. So this is, it will be similar. Okay, for liquid phase kx will be this term dab rho by m average by delta, kl prime, that will be your this. Okay, and the conversion is kc and ky. Okay, so if you multiply by rt by p, then it will be delta. So this is the conversion factor, kc prime equal to rt kg prime, kx prime equal to this into kl prime equal to CL. Okay, so there are 5 mass transfer coefficient for diffusion of A through non-diffusing B, and another 5 mass transfer coefficient for equimolar counter. And these are the expression, and depending on your problem, you have to select the correct mass transfer coefficient. But in your problem in mass transfer, you are getting reported in someone other one. Let's take, I just told the mass transfer whatever is presented there, but then you can calculate the mass transfer what way you want using these relations. Okay, so that thing you have to deal with in mass transfer. That is the, you have to deal with 10 mass transfer coefficient, but heat transfer coefficient, in heat transfer you have dealt with one heat transfer coefficient, but here you have to deal with this thing. Here you need a little bit practice. If you don't do practice in pen and paper, it will not be with you, and then you cannot do it. So key thing is, what are these equation? This is the equation for equimolar counter diffusion, and this is the equations for the diffusion of A through non-diffusion. If you can remember this thing, if you make some practice, then other things will come automatically. Okay, so if you take this summary, okay, when for diffusion of A through non-diffusing B, that NA flux is equal to kg PA minus PT, what a kg is equal to this expression. Okay, and what is the unit of this? Kg will be flux by delta P. Flux mole time per area means meters per second, area by delta P. Okay, when it is Ky, that is the expression, and this will be, in case of delta P, this will be delta Y. And in case of when Kc, that this is the expression, and corresponding here mole time, that is the flux by air, that is by delta C. Na equal to Kc, so by delta C. Okay. So similarly for equimolar counter diffusion for gas phase, okay, that Kg prime Pa minus Kg prime equal to this Ky prime Y minus Y2, where Ky prime is dAb P by this expression, already we have derived this one, and Kc dash will be this one. But important aspect you have to note here, that is the unit of mass transfer coefficient. Sometimes in your problem statement they will not tell explicitly that is Kg or this is Kc or Ky, but you have to, the mass transfer coefficient is 0.52 mole per time area delta P. If it is delta P, then you have to understand that it is the mass transfer coefficient where that driving force is in terms of partial pressure, means you have to do this. Sometimes they will tell you have to see the unit. From the unit also you can understand what is the mass transfer coefficient. This thing always they will tell the mass transfer coefficient is 0.5 to a delta C. When you see this delta C, mole time area delta C means that means you have to understand this is the Kc. Already you know that if for a problem, how will you understand whether this problem is diffusion of A through non-diffusing or equivalent. That already we have discussed. Here I am telling what is the mass transfer coefficient. Okay. Sometimes it will not, or a Kg, Ky, Kc, it will not be told explicitly, but from sometimes you have to understand this from its units. Similarly, for liquid phase, Kl equal to Ca1 minus Ca2, okay, or Kl equal to this, Kx into x1 minus x2, Kx equal to this. And for equimolar counter diffusion, Kl prime, that will be Ca minus Ca2, or Kl dash equal to this, and Kx prime xa1 minus xa2, this, and these are the conversion factor. Okay, so this part you have to understand. In mass transfer you have to deal with two type of mass transfer coefficients, because driving force and what is the type of mass transfer depending on the, and there are some changes. But if you know one mass transfer coefficient, other mass transfer coefficient can be calculated from this relation. Apart from this, there are another type of thing, that is driving force. Already I told that is the driving force is mole ratio. Okay, when that is I denoted the capital A1 by capital A2, number of moles A, number of speed. So Na equal to small k, that will be capital Y for gas phase, and for liquid phase that will be Na equal to small k capital X, x1, x2. Now what is relation between the mole ratio and mole fraction? This is the mole ratio, moles of A by moles of B. Now this is the mole fraction of A, and 1 minus 1, that will be the mole fraction of B. So this mole fraction of A, because x yn plus yb equal to 1, so yb will be 1 minus y, the mole fraction of A by mole fraction of B, okay, that is the mole ratio. And if you make the simple calculation, then mole fraction Ya will be capital Y by 1 1. Similarly, it will be for the liquid case. See, this mole ratio concept is very important. Later you will understand when you will apply these theories in our mass transfer equation. Most of the time we will use this mole ratio. There are some certain advantages, and here I am introducing the part, but what are the advantages later we will see. Okay, so these are another type of mass transfer coefficient, that is capital Ky, capital Kx, where the driving forces are in terms of mole ratios. There is a difference between mole ratio and mole fraction. Now another mass transfer coefficient, that is the F type of mass transfer. Now what is the, see, already I have done this thing. For if you see, this is my Na equal to Na plus Nb, Pa minus P minus dA by RT dP by dt. This is the governing equation of mass transfer. Then we apply this for, one is for diffusion of A through non-diffusing B. That time we take Nb equal to 0 and we derive this thing. And another one, equimolar term, then Na equal to minus N. Then this part cancel out, we derive this thing. Okay, but if you don't consider if I consider this as a generic equation, then after you start if you start with this equation and without any particular case, we solve this equation directly, and which will be applicable for both equimolar counter diffusion and diffusion of A3, and then it will finally this equation will come: Na equal to Na plus Nb dAb P by RT delta ln Na divided by Na plus Nb minus y2 Na divided by Na plus Nb minus y11, and then this, what is this thing, that is called F type of mass transfer coefficient, and this F type of mass transfer coefficient is more generic. Now let's see how this expression will come from this equation, because we not take anything whether it is equimolar counter diffusion or diffusion error. We just directly solve this problem. Now if you see, if you take this equation, we know this is the governing equation, then A equal to PA by, I convert this in terms of Y, because this expression is in terms of mole fraction. So PA minus P equal to YA, we know dPA equal to YA in capital P, so that P will come RT dYA dz. Now if you take this is this side, okay, Na plus Nb minus Na, and this will take side, then dAb P by RT dy dz. Now if you take the Na1, Na plus Nb divided by, so Ya Na by Na plus Nb, this will be 1 by Na plus Nb into this term, so dAb into P RT dy by dz. Now if I multiply it with Na, so Na okay, now you divide with this, okay, then if you multiply it, now we just I take the one negative sign, so if I take one negative sign, Na by Nb, okay, minus Y, and this will be negative term. Now this dz, okay, minus Na by Nb dAb P by RT, now this dYA Na plus Nb minus Y, so this will be my term. Okay, this term will come here. Now I will integrate this 0 to delta, where Ya1 to Ya2. So if I know this is the only the Y1, so that will come 0 to delta dz, okay. So this Y1 minus sign 1 by this into dAbP, that will be 1 Na by Na plus Nb Y2, that is a limit, this will be this. So now if you multiply it with Na equal to Na by Na plus Nb dAbP by RT delta, delta will come here, ln Na by Na plus Nb minus Y2 divided by Na by Na plus Nb minus Y. So now if you see, this is this expression is this expression. So then this expression is coming from my governing equation of mass transfer without any special case. I have not considered this is for whether it is equimolar counter diffusion or it is diffusion of a diffusion. That's why this equation is valid for both. Okay. So and this is your Fg. So Fg will be dAb P RT delta. Now you can remember Kg, what this was the expression. DABP RT delta. So PBM, so FG equal to KGP. Okay, for equimolar counter diffusion, FG will be Kg dash P. Okay, so in this lecture we discuss with the different type of mass transfer coefficients, and always and we express this different type of mass transfer coefficient, and there is a one term is always there, that is the boundary layer thickness delta. Okay, so if I can calculate this boundary layer delta, then other terms will be easily calculated. So there are 5 mass transfer coefficients for diffusion of A through non-diffusing B, and another 5 mass transfer coefficient that we denoted as a prime, that is for equimolar counter diffusion. And thereafter we have seen what are the expression of different type of mass transfer and what are the relation between the different type of mass transfer. Then we define one mass transfer coefficient that is based on mole ratio, small k capital Y, small k capital X, and finally we have derived one F type of mass transfer coefficient. Okay, so today let's stop here. Thank you for your attention.